Well, folks, thank you for joining us for another one of our weekly TESS seminars. TESS, of course, is our Center for Tropical Environmental and Sustainability Science here at JCU. And I think we've been operating for 10 years now, and we're pretty happy with the way TESS is going overall. Huge kudos, as always, to Yoko Ishida and Nina Taylor and Andrew Gray Spence for keeping everything running, which is not a trivial thing to be doing around here in the age of modern telecommunications. It's a real pleasure to introduce Brooke Williams. I met Brooke a couple weeks ago back at UQ, and one of the things that Yoko sent me to Brisbane with was basically an invitation list to find seminar speakers. So I dutifully said, yes, ma'am. And Brooke was the first victim who's managed to show up here so far. So Brooke's a lifelong Queenslander. She was born and raised in Ayr, which is like halfway down the coast. It's just a curious coincidence. I'm not saying anything more than that Ayr is where the cane toad was released. Now, I'm not implying anything. I'm just pointing out the coincidence involved there. Okay, so Brooke has been completely trained at UQ, of course, which is a very fine university, and especially in fields like environment and ecology. Very, very dynamic group there. She got her undergraduate degree, her honors, and her PhD all at UQ. I'll let her tell you a little bit more about the specifics of that, but she's working on a lot of important issues, assessing the state of planning for conservation of intact ecosystems. And she's worked in many different parts of the world, Latin America and Africa, and of course here in Australia. So she's got a lot of interesting insights, a lot of interesting things to say. We'll turn things over to Brooke. Thank you.
Hi, everyone. Thanks so much for having me, and especially thank you, Yoko, for organizing everything to get me here. It's great to have the opportunity to come talk to you all. So I'm a postdoc at the University of Queensland. I'm going to be talking to you today mainly about the work that I carried out during my PhD, which was called Assessing the State and Planning for the Conservation of Intact Ecosystems. So, firstly, why are intact ecosystems so important? We know that they're crucial for maintaining biodiversity and providing us with ecosystem services. So intact ecosystems hold some of the last strongholds of some really threatened species. And they're really our life support system. So we rely on them for our survival. We're currently, as many of us may have noticed, experiencing the consequences of their loss. So we're seeing increases in climate change. We're seeing increased frequency of fire, intensity and frequency. The floods that we recently saw in Brisbane and in New South Wales. And some people have even started attributing us pushing further and further into these intact ecosystems and linking that to COVID-19 and possibly future pandemics. But how do you identify where an intact ecosystem is, or what is one? So ecological systems are really complex. They're made of so many different characteristics, and to properly measure ecosystem integrity, you really need to include measures of ecosystem composition, structure, and function. There's a lot of different categories under each of those. And you need to know current and reference conditions, which is really difficult to quantify. And none of this has been effectively quantified at a broad scale before. And this is a problem because to ensure that management actions and policy decisions are implemented effectively, we really need to know the status and trends of ecosystems. We need to know where the intact ones are so that we can conserve them, where the degraded ones are so we can restore them. We'll never fully be able to accurately measure ecological integrity 100%. So in lieu of being able to do that, informal scientific surveys of ecological condition, proxy indicators are increasingly used to inform on initial assessments for planning purposes. So this importance has given rise to something called human pressure maps. So human pressure maps take pressures that we know damage the environment across Earth and basically adds them up cumulatively to get a relative measure of human pressure across Earth. And there's a lot of positive actions that humans implement on the environment, like restoration. In Australia, to keep an ecosystem intact, you really need management. You need people to implement fire regimes. So there's a lot of positive actions that people implement, but these human pressure maps typically quantify negative impacts. So this gives us a relative measure of how degraded or intact an ecosystem or parcel might be. So there's been a lot of mapping efforts that have tried to map intact ecosystems recently. Similar but different methods. And one recent study, which was by Riggio et al. In 2020, they did a comparison of all of these, or 4 of the main methods of mapping intact ecosystems. And although there were differences among them, they found that on average, around a quarter of terrestrial Earth could be considered under low human influence. So different, but generally the different mapping efforts had similar answers. So the overarching objective of my PhD was to provide up-to-date measures of human pressure across ecosystems, to provide new metrics to quantify human pressure, and to use this type of information to help develop planning frameworks that support the conservation of Earth's intact ecosystems. So I'm going to focus on 3 chapters in particular today, 2 global analyses and then 1 local or more local case study. And I'm going to talk to you about some other work I did during my PhD and what I'm moving into over the next 3 years. So the key messages that I want you to keep in mind for this talk, the key take-home messages is that intact ecosystems continue to be rapidly lost, even though they're super important. Global conservation efforts urgently need to focus on retaining the few intact ecosystems and restoring those that are degraded. And there are increasing solutions and opportunities available for positive action through spatial planning. So those are my key things to keep in mind. The first analysis that I'm going to talk to you about is called Change in Terrestrial Human Footprint Drives Continued Loss of Intact Ecosystems. So we published this in One Earth, and it got quite quite good in the media. We got tweeted by Greta, which was very exciting for us. So we used the human footprint maps. So you might have heard about the human footprint maps. I think, so the first was done by Eric Sanderson, the second by Oscar Venter when he was working under Bill Lawrence, and then we released the updated version of these human footprint maps. So they're a type of human pressure map, possibly, one of the most widely used. So our maps covered the years 2000, 2005, 2010, 2013, and they include 8 human pressures. So using these maps, we basically quantified the loss of intact and wilderness areas, but we first had to classify these maps by these ecologically relevant scores. So a human pressure score of under 4 has been shown previously to be ecologically relevant for species. Above this threshold, it's been shown in previous studies that species extinction risk dramatically increases. So these thresholds, there's different studies that have used these thresholds throughout the literature. But we're talking about the least, so the human pressure spectrum, it's a spectrum, right? The intact and wilderness areas are at the end of that spectrum. So they're the least damaged or the least influenced by human pressure. So we use these delineations to assess the current state and rate of change in human pressure at the global, biome, eco-regional, and national scales between 2000 and 2013, using the new human footprint maps. So we found, concerningly, that around 19% of Earth's terrestrial surface deteriorated, so human pressure increased, while only 6% improved, so human pressure decreased. This increase in human pressure, we found it to be so substantial across 1.89 million kilometers squared of Earth's intact lands, so those areas that were under that important threshold of a value of 4, an area approximately the size of Mexico crossed that threshold into the modified category. So it's quite a lot of land that went from being in a relatively intact state to a modified state. So we assessed the current state of Earth's terrestrial biomes, and we found that tropical and subtropical grasslands, savannas, and shrublands lost the most intact area, but the rainforests of Southeast Asia also underwent rapid modification. We found Russia, Canada, Brazil, and Australia are responsible for the largest areas of the remaining intact areas. And between that time period, the DRC lost more intact land than any other. This was followed by Indonesia and Brazil, which also lost high amounts of intact lands. So if we know that intact ecosystems are so important, why are we losing them so rapidly? There's a lot of reasons why, but there were some key failures in policy mechanisms, or some opportunities for intact ecosystem conservation in the past, which were possibly overlooked. For example, the SDGs talk about protection, restoration, and sustainable management, but condition of an ecosystem was never mentioned. The UNFCCC aimed to mitigate climate change. However, there was no mention in that framework about intact ecosystem conservation. The Rio Declaration is another biodiversity-focused declaration. It did not mention intact ecosystems. AET Target 11 from the CBD, Convention on Biological Diversity Strategic Plan, they set protection targets for the land and sea, but again, there was no qualifier of that those areas needed to be of a certain integrity or anything like that. And many of those IET targets were dependent on ecosystems, but explicit references were dispersed among the targets for ecosystem types. So there was a few missed opportunities in our conservation and environmental policies. But the good news is that intact ecosystems are increasingly being recognized as important. So target 1 of the first draft of the Convention of Biological Diversity's Global Biodiversity Framework, which is the successor to the strategic plan with the IET targets, it specifically states that all land and sea areas globally should be under integrated biodiversity inclusive spatial planning, addressing land and sea use change, and retaining existing intact and wilderness areas. So we've got our intact and wilderness areas included for now. It's not finalized, but they're in the first draft. So we're making progress. And these were all of the co-authors involved in the study, so big acknowledgement to them. So the second global analysis that I'm going to talk to you about is the global rarity of intact coastal regions, which was recently published in Conservation Biology. So as many of us know, coastal regions encompass some of Earth's most important ecosystems like coral reefs, seagrasses, mangroves. They're really important for biodiversity and ecosystem services, such as carbon sequestration, food provision, storm protection. We know that they're very important, but coastal regions are continuing to be degraded by things like development, which is resulting in profound losses of biodiversity and ecosystem services. So separately, for the land and for the sea, there have been assessments done of trying to identify these intact and wilderness areas. But the land and sea are connected. So they're connected through many biological mechanisms, through nutrient flows, through runoff. It's really important that if you're doing a coastal assessment, you really need to account for that land and sea connectivity. So the fact that these assessments have been carried out previously, separately, in the past means that coastal regions haven't really been considered in these sort of analyses before. So we took the recent, or 2013, the most recent human footprint map, and the cumulative human impact map, which is the marine equivalent, which is also only goes up to the year 2013. And we, for the first time, brought them together to try and get an assessment of coastal region intactness. So what we did was we allocated a point along every 1 kilometer of the coastline. And we basically said, okay, within the coastal region for each point, what are the intactness scores? How intact is each point? And we created sort of an intactness metric across coastal regions. Using this metric, we were able to look at different units to try and understand coastal region intactness. We found that no coastal region is 100% free from human influence, and only around 15% of all coastal regions can be considered low in anthropogenic pressure. Around 14% is exposed to extreme human pressure, so 0% intact, and around 50% are exposed to pretty high levels of human pressure, less than 20% intact. So we found most of the intact coastal regions are located in Canada, Russia, and Greenland, but we also identified large expanses of relatively intact coastal regions in Chile, Australia, the US, Svalbard, Indonesia, in quite a few important places. So there still are some areas that do remain pretty intact. We also assessed our intactness metric across ecosystems, and we found human pressure is greatest across the coastal regions with seagrasses, savanna, and coral reefs, whereas deserts, forests, and salt marshes, they're less affected by human pressure, but still quite high. So we also looked at protected areas across coastal regions, and of the coastal regions that are protected, around 43% are under relatively high levels of human pressure. So our key results are to say it's safe to say that intact coastal regions are now quite rare. So this has a lot of implications for management and conservation. Many of the coastal regions that remain intact are at those higher latitudes. So our paper is really a message about restoration as much as it is about retaining those areas that do remain intact. So broad scale restoration is really necessary across coastal regions. Where and how to restore, protect, and manage areas varies depending on the levels of human pressure that we're experiencing, which is something that our global metric can help answer. Around 16% of coastal regions are under formal protection, but a lot of these are under high levels of human pressure. So that is also quite high. Encouragingly, we found that around 60% of coastal regions are protected in both the land and marine environments. So if you're protecting just one environment, you might be missing out on a lot of threats that might come from the other realms. So it's really important that both are managed together, and we did find that at around 60% that's possibly happening, which is good news. Again, these are the co-authors, and lots of work went into it, so a big shout out to all of them. So I'd like to come back to target 1 of the first draft of the Convention of the CBD's Global Biodiversity Framework. So it talks about retaining existing intact and wilderness areas, but it also talks about the importance of spatial planning. So spatial planning is also increasingly recognized as being crucial to conservation action. It's been around for a long time, but it's still important, and it's getting even more important, I think, which I think I'll convince you of during this talk. So intact landscapes and structured decision making. So spatial planning is essentially the effective allocation of conservation action. Many of you are probably familiar with it, but it is typically used or solved using optimization problems and optimization tools like mark-sand zonation, for example. But many existing decision support frameworks in spatial conservation planning are designed to identify priorities within already fragmented landscapes. There are a few examples that seek to mitigate harm within intact landscapes. For example, there's something called the development by design approach, but there are very few spatial planning frameworks out there that have been developed specifically for intact ecosystem contexts. So I'm going to now talk to you about a chapter of my PhD where we did develop a framework for a relatively intact landscape. So it's called Minimizing the Loss of Biodiversity and Ecosystem Services in an Intact Landscape Under Risk of Rapid Agricultural Development. And this was published in Environmental Research Letters. So it was part of a SNAP, a Science for Nature and People partnership project involving many NGOs, and I'll acknowledge them at the end, but it's for the Orinoco region of Colombia. So it's a really beautiful tropical savanna environment. It's the second largest savanna system in South America. And until recently, relatively recently now, it has been off limits for development because it was largely occupied by a guerrilla group. But because of the peace agreement in 2016, this has kind of promoted its development. So it remained relatively intact. Still, there was agricultural development into it, but it is now, or was, and is still being targeted for agricultural development. And it's also incredibly biodiverse and provides a lot of important ecosystem services to local people and to the world. So since the peace agreement, this is all it's been targeted. These are some of the amazing species that are found there. So you can see it's incredibly diverse. Until recently, the most common agricultural land use was this broad-scale cattle ranching, which was relatively not that damaging for the environment. So broad scale, not very high intensity. And the traditional management kind of made this compatible largely with the landscape. However, it is now being overtaken by large-scale plantations such as oil palm is a really big one. This is a photo I took when I was there. So there's heaps of oil palm plantations and other agricultural interests popping up in the region. So the research questions that we wanted to answer in this project were, what are the potential impacts of conversion of natural ecosystems to agriculture on biodiversity and ecosystem services? And how, if it's at all possible, can spatial planning reduce the negative environmental impacts? So we set about developing a land use planning framework that addresses the decision-making required when you open up a relatively intact landscape for development. So the first question we had to ask is, how much of this area are people in the region, or are they willing to let go of? We explored different targets of the region, but everything can be manipulated. It's a very flexible framework. We had to define the objectives of the region, which were under agricultural goals, which were to expand agriculture, maximize profit, And then we had the environmental goals of minimizing local species extinction, meeting ecosystem retention targets, minimizing water and carbon loss. We defined the main land use options of the region, which were agricultural land uses, and then one land use which was do not develop into, so that the ecosystem would remain natural. And then land use allocation, we had to solve the problem of how can we possibly achieve all of these multiple objectives at the same time. So this is our land use planning framework. It looks a little bit complicated, but to the left we have all of the things that we care about, all of our input data and our objectives, and they go into our optimization problem, which also has constraints of ecosystem retention targets, so targets that you definitely can't develop into, agricultural expansion targets, how much agriculture do we need to expand, and then relative weights that are adjustable for each of our objectives. And we use these relative weights to create trade-offs, to assess the trade-offs between the competing objectives within the region. So our outputs were in the form of maps and trade-off curves. So spatially explicit land use planning solutions and trade-off curves to try and find those compromises between objectives. So that's a little bit complicated. So let's walk through one example of a scenario together. So we've got an increased demand for agricultural product. We know that there's an opportunity here in the region. So we say, okay, we know that we want to develop 20% of this relatively intact landscape, which equates to around 10,000 kilometers squared of each commodity. So that's our agriculture objective. But at the same time, we have our environmental objectives. We really care about the biodiversity and ecosystem services of the region, so we need to consider them together. So in this example that we're walking through, we have our agricultural goals of expanding agriculture to meet 20% of the region. We want to maximize profit. We have to ask ourselves, how much do we care about profit and the environment against each other? In this situation, we care about them equally. And finally, we have to ask ourselves, how much do we care about these environmental objectives relative to each other? In this case, we'll say we care about them equally, but you can adjust this in the framework. So if you only care about biodiversity, you could assess that. And then we ask ourselves if we care about retaining different ecosystem types. In this case, we say yes, we set targets for our ecosystems at 50% of their historical range. We run this through our spatial planning, through our optimization problem, and then we get our answers in the form of spatially explicit solutions. So this is the current distribution of land uses. So it was, when I did the analysis, there has been an update to this map now, but at the time of this analysis, this was the distribution of land uses, and you can see it's relatively intact. And our planning framework would allocate those land uses based on what you define your objectives to be. So that's the solution from the problem that we just walked through. But a map is nothing without knowing how good or bad that map or that solution is performing relative to the best and worst case that you could possibly get. So this is a trade-off curve, and each point on this trade-off curve represents a different spatially explicit solution. So here's our example where we set, in this example, it was equal weighting between the environment and our agricultural objectives. So it's somewhere in the middle of the curve. But if we only care about maximizing agricultural profit or production value, that's what our spatially explicit solution would look like. If we only care about species persistence, that's what our map would look like. So we can assess these spatially explicit solutions relative to each other and assess the trade-offs between them. In this example, by reducing production value by 2%, we increased species persistence by 8%. So in that way, we can find compromises between solutions and between our objectives. So we also assessed in our framework species persistence, but also carbon loss and water loss. So we were able to find compromise solutions that can increase the loss of these ecosystem services by a slight reduction in agricultural production value. We also, so as I said before, we assessed different thresholds of loss. This is flexible and could be manipulated and changed to any other thresholds. We found that there are trade-offs between agricultural profit and environmental goals, which indicates that if you let go of a little bit of agricultural benefit, you can reduce negative impacts on the environment. However, there are still negative impacts which are unavoidable through development. So the key messages from this study are that in the Orinoco region, spatial planning can reduce but not mitigate negative impacts, negative environmental impacts from loss of native vegetation. Our framework has the potential to ensure that agricultural expansion goals are met while minimizing environmental damage as much as possible. And it can be translated into any other environment that's being opened up for development, where development isn't unfortunately inevitable. So again, these are the co-authors and all the people who contributed to the paper, and it was part of a SNAP project involving WCS, TNC, and SEAT, with a lot of people on the ground in the Orinoco region. So back to our important goal, our first target, our target one of the first draft of the CBD's Global Biodiversity Framework. Talking about spatial planning, I would just like to highlight the importance of spatial planning from here on out. I think moving forward. So during my PhD, I had the brilliant opportunity to work on 2 different spatial planning platforms that were online. So there's a big push to have more spatial planning tools available, more data available in the cloud. So, you know, Google and Microsoft are really trying to democratize spatial planning and make it available to the masses. So I had the opportunity to work with on this restoration planning platform called We Plan Forests, which is one of the ones up here in the top left. But the other one I had the privilege of working on is probably more well known. So MarkSan is the most widely used decision support tool out there. It's planned around more than 5% of the planet in over 100 countries, and it was kind of validated at UQ. So of course, I've worked on MarkSan coming from UQ. But a really exciting project that's happening right now is that MarkSan has always been run on a desktop, right? And it's a little bit tricky to use. So it's kind of easy if you have studied spatial planning at university and things like that. But if you're a decision maker in the government, it's really hard to overcome that technical barrier, which means if you're not using spatial planning tools, you're probably making decisions suboptimally or in a worse way than they possibly could be made, right? So this initiative is bringing MarkSan to the cloud along with these other tools. It's bringing MarkSan into the era of cloud computing. So MarkSan is coming onto the Microsoft Azure platform. So it has a wizard and help guide to help new users along. So it's very easy to use, and it's going to be a key application of Microsoft's planetary computer, which is very exciting. So through this collaboration with Microsoft, this is the landing page. So it's going to be available in May for, I guess it's not really targeted at people who have the technical skills, but more about democratizing it, making spatial planning available for the masses. And it's got a central project dashboard where you can make your project, you can allocate collaborator roles. So you could do your spatial plan and then you could share it with stakeholders and have them look at only the solutions rather than all of the technical bits that they could comment on. So it's really going to bring spatial planning front and center, making it available to so many people where they might not have had access. So I really think that spatial planning is being recognized as important, and there's going to be a lot of more and better spatial planning tools available, with maybe Marxam being the starting point, and probably more frameworks will come online in the future, I expect. So very exciting place for spatial planning, I think. And that project came about with a collaboration between all of these people, but largely driven by the Nature Conservancy and Microsoft. So that is kind of a brief highlight of all of my PhD work. So I'd just like to let you know what I'm going to be working on for the next 3 years. So I've started a postdoc with the Sustainable Landscapes Group, again at the University of Queensland under Jonathan Rhodes. So we're going to be working on supporting decision-making on private lands in New South Wales. So again, working with spatial planning and developing a decision support framework in a really collaborative way with many of the actors in New South Wales. There's a particular focus on koalas, which have just been marked or regarded as endangered in New South Wales, unfortunately. So there's a big push to try and bring into some social variables into a novel spatial planning framework to help guide decision making about where to invest in private land conservation in New South Wales. And I'm also going to be working on modeling global ecosystem service flows and trying to improve policy and decision making around ecosystem service use, and possibly informing on policy that could improve to make sure we don't lose as many ecosystem services as we are. So all about decision making again, and developing these decision support tools to support that process, with a particular focus on global trade. So a lot of interesting things, and if you're interested in those topics or anything I've talked about, please feel free to reach out to me at any time. And coming back to those key messages, I think I've convinced you that intact ecosystems continue to be lost. We need to focus on retaining and restoring them. And that spatial planning, there's plenty of solutions and opportunities out there. So thank you so much for coming along and inviting me. It was great to come to the campus and meet you all.